it will be P will change to, this is a positron, right?
But what is the name of this particular reaction?
It's a beta reaction. Okay, so in beta reactions you can have beta positive and beta negative. So the positron or the electron. So the maximum energy of the positron is a measure of the energy difference between the two nuclei. Okay, so this is in your book. You can also study it from there. The second method would be the energy difference can be measured through nuclear reactions. Nuclear reactions. So, for example, if you have boron 11, right, and you bombard it by protons, okay, so you will have, this is P for proton plus boron 11, and you can have a reaction like this. Okay, so this can be also a way in which you can again analyze this reaction and the energies on both sides of the equation, and you can find the proton energy required to cause this reaction and then measure the energy difference between boron 11 and carbon 11. And then you have a figure in your book that represents such an experiment, and in this case it was found that if you take A 2/3 on this side and you take this Coulomb energy on this side, you get a graph, let us say something like this. So, this is properly marked in the book. Okay, I switched that off because it was causing a glare, right, but you can see it in your book, and this is the graph on page 55. Okay, you can see it here, and you can see that there are many different, this experiment has been done for many different nuclei and the energies have been plotted, right. And so, what was the conclusion of these experiments? When they did these measurements, they found that this difference in Coulomb energy delta EC is proportional to, if you have a straight line, it means that it is proportional, right. It is proportional towards, it is proportional to the mass number raised to 2/3. So, this means that the radius is proportional to A raised to 2/3, right. And you remember last time in the previous classes we studied an equation where we had R is equal to R naught A raised to 1/3, where R naught was a constant. So, therefore, the slope of this line will give you R naught. And this has a value that ranges from 1.2 to 1.25 femtometers. So, this is another way that the radius of this nucleus was determined. Now, another thing that we have to understand is that, you know, nuclear matter itself can lead you, charge can lead you to an understanding of the size of a nucleus, right. The presence of matter itself can lead you to an understanding, right. So, in this case what happened is, so these are different experiments that were done over time by different scientists, and we are reading the conclusions of those experiments, right, and then the conclusions that were derived from those experiments, and many of these scientists got very Nobel prizes because they did some breakthrough work while performing these experiments. But of course, this was not so easy or so short. In fact, whenever, as you know, you are performing experiments, there are a lot of challenges and limitations, and many a times your experiments fail or whatever happens, and you have to rethink about what you are doing. And so, but we are lucky to have the conclusions of those experiments, right. So, that is what we are discussing. So, now there is another experiment in which a alpha particle is scattered from a gold foil. So, What is an alpha particle? It's a helium nucleus, right? So, alpha particle is a helium nucleus. Yes, this is the famous Rutherford experiment, and Rutherford in fact got a Nobel, I think, for this experiment because he discovered the nucleus using this experiment. So, this experiment is also known as the Rutherford scattering, and there is a formula associated with that, there is a long calculation and a derivation associated with that. We will not go into too much detail, but we will only study the part where we understand the nucleus, right. Okay. So, the difference you can see between the reaction, the incoming particle is the alpha and it is striking a gold foil. You can see different diagrams. Again, if I switch this on, there are many different figures in which you can see this experiment, how he used polonium to produce emit an alpha particle which was then bombarded on a gold foil, and then he studied how the radiation was scattering from this, and then measuring the angle of the radiation he was able to calculate and predict the nucleus. Okay. Now, so this detail again you can see it, I have also written the Rutherford scattering formula here. So, you have it in your book as well. So, this is so, in this case theta is the scattering angle. Okay. In fact, in some books you have theta and in some books you have phi. Okay. So, and sigma is known as the scattering cross section. Are you familiar with the term cross section?
Yes.
Oh, no, not this one. In nuclear cross section means something else. I know the cross section you are talking about. Huh?
Certain angle where from
No, no. When we talk about cross section in nuclear, we will study this in detail later on. Okay. Cross section is a term we use to explain the probability of the occurrence of a reaction. Okay, we will define this later. Okay.
Probability of occurrence of a reaction? Or
Of a reaction, for example, fission. Fission is a reaction.
how do you find its probability? Like,
Yeah,
do
every.
you have a wave equation for that?
Not really a wave equation because again, okay, I do not want to spend too much time on this because this is a topic that comes later on. Right now I just talked about it because it was in the equation. Cross section is, you can find tables in the book where you can get the values for the cross sections. For example, if fission is supposed to happen, do you use U238 or do you use U235?
U235.
And why?
It's because it's unstable and it easily, but when
Okay,
it
so,
it converts into a xenon. And
so one of the reasons is that the cross section for fission is higher for, you understand this? Yeah, that's what we mean by the probability of a reaction. Okay. So this is a small sigma. We also have other symbols like capital sigma, so and so on and so forth. We don't want to go too much into that at the moment, but anyway, it's the probability of the occurrence of a reaction. Okay. So again, omega, as you know, is normally used for solid angle because of course it's happening in a certain angle, but it's in a 3D. So a normal angle in 2D is just something like this, but then in actual reactions it's scattering everywhere, yeah, like a cone. Okay, and then phi is the deflection angle or the scattering angle, and B in this case is defined as a parameter that represents the impact. Okay, so again there are other terminologies also that are sometimes used. Okay. So we don't want to go too much into this because we are in the beginning of the course and we don't want to go into the derivation or something like that. But anyway, this is the basic method that was used for the determination of the